Imagine you're steering something: a spacecraft, a thermostat, a savings account you're trying to grow. At every moment, it sits in some condition. Call that condition the state and label it X. You get to nudge it. Each nudge is a decision, a control, and we'll write it U. Every decision costs something. Add those costs up, and the total is what we call J. The whole game is to choose your controls so that J comes out as small as possible. Now, here's the fork that matters. You could write your entire plan in advance. Do this, then this, then this. That's an open loop plan. But the world drifts. One gust, one surprise, and your pre written script is steering for a world that no longer exists. The better object is a rule. For whatever state you find yourself in, at whatever time, it hands you the single best move. We write it u star of t equals f of x and t. That's a feedback law, a control law, and it is the real prize. So the question of this whole film is easy to ask and hard to answer. How do you find that rule? Here is the one idea the whole method rests on. It is almost too simple to trust. Suppose somebody hands you the cheapest possible route from a start point A to an end point E. Now put your finger down anywhere along it. Call that spot B. The route falls into two pieces, getting from A to B and getting from B to E. The total cost is just the first piece plus the second. Claim that second piece from B to E must itself be the cheapest way to get from B to E. Why? Suppose it weren't. Suppose some sneakier path from B to E were cheaper. Then you could splice it in. Keep A to B but take the cheaper tail, and your new route from A to E would beat the one you were promised was best. That's a contradiction. So the cheap tail was optimal all along. Bellman said it like this: an optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions must form an optimal policy with regard to the state resulting from the first decision. Read it twice. Every optimal plan is built out of optimal subplans. That is the principle of optimality. Watch what that idea buys us. It shrinks a giant planning problem down to a tiny one. Say you're standing at a point B and you've already been handed the cheapest cost to finish the trip from each place one step away, from C, from D, from E. Those are your downstream optimums. Then your only job at B is to pick the next hop. For each option, add the cost of that single step to the best you can do from wherever it drops you. Compare the handful of totals. The smallest one is the optimal decision at B, full stop. You never replan the whole journey. You make one decision and you trust the optimum beyond it. Do that at every point in the right order and the entire problem falls. Let's make it concrete with the example Kirk uses: a motorist and a road map. You're at intersection A. You want to reach H up in the corner as cheaply as you can. The streets are one way. The arrows show which way you're allowed to drive, and every block has a price painted on it. Gas, tolls, minutes, whatever you like. The brute force instinct is to list every legal route from A to H, total each one, and keep the winner. On a map this small, you might get away with it, but the number of routes explodes the moment the map grows. That road is a dead end. Dynamic programming refuses to enumerate. Instead, it does something that sounds backwards and is. It starts at the destination, at H, and works its way home toward A. Watch. Start at the end. The cost to reach H from H is nothing, 0. That is our seed. Step 1, block back. From G, there's only one legal move, north, into H, for a price of 2. So G's cheapest cost to finish is 2. Write it on G in gold. From F, one move east to G costs 3, plus G's 2 makes 5. Now the first real choice. From E, you can drive straight east into H for 8 or dip south to F for 2 and inherit F's 5, which totals 7. 7 beats 8. So E's cost to go is 7 and its optimal heading is south. Notice what we just did. We reused F's answer instead of recomputing it. That reuse is the whole secret. Keep going. D is 3 plus 7, 10. At C, another fork. North to D is 5 plus 10, 15. East to F is 3 plus 5, 8. 8 wins. B is 9 plus 8, 17. And finally A. East to D is 8 plus 10, 18. South to B is 5 plus 17, 22. 18 wins. Follow the green. A, D, E, F, G, H. 18. The cheapest trip on the map. And look at A's tempting shortcut south. Its first block is cheaper, 5 against 8, but it leads to 22. Greed loses. We solved from the end and reused every sub-answer. That is dynamic programming. The roadmap was never really about roads. Swap its pieces for a real system. Each intersection becomes a state. The condition the system is in are X. Each heading becomes a control, a decision, are U. Same skeleton, but there's a catch, and it's the whole reason this part feels tricky. On the map, there were just 8 intersections, a handful of places to be. A real system isn't like that. Its state can be any value in a range. Here, any number from 0 to 1.5. Not 8 values, infinitely many. And the control too, anything from -1 to +1. Now remember how we solved the map. At each place, we tried every move. But you cannot try every move when there are infinitely many states and infinitely many controls. The method would never finish. So we do the only sensible thing. We sample. Instead of every possible state, we pick just a few. 0, a half, 1, 1.5. Instead of every control, a few. -1, -0.5, 0, a half, 1. Like checking a soup at a few temperatures instead of all of them. That handful of chosen values is the grid. Now picture it. Time runs left to right in stages. The chosen states stack upward. Every crossing is a dot, and each dot means one concrete thing. The system is in this state at this stage. This one here, state 1 at stage 1. And look what we've rebuilt. Each dot is an intersection. Each control is a road, from a dot now to a dot one stage later. We've turned the system back into a map, one we can finally solve. So let's solve it, exactly like the map, from the end backward. Here's our tiny system. The next state is just the current state plus the control. And the cost is the final state squared plus a small penalty for every control we spend. 2 stages, then we are done. Start at the last stage. Pick one dot. Say the state is 1.5 with one move left. Try each control in turn. Each one is a road to some dot in the final column, and each carries a cost. The penalty for that control plus the squared final state it leaves you in. Compute them all and keep the cheapest. Here the winner is -0.5, costing 1.5. Paint that cheapest cost on the dot in gold. That gold number is the cost to go, the best you can possibly do from here. Now do the very same thing at every dot in that stage. Each one earns its own gold cost to go. The last stage is solved. Then back up one stage, and here is the magic. From a dot at stage 0, you try each control again. But you do not resolve the rest of the trip. You simply add this step's penalty to the gold number already sitting on the dot you land on. Reuse, never recompute. For state 1.5, the best move costs a half now and lands where the gold already reads 0.75, total 1.25. Solve from the end. Reuse every gold answer. That is how the grid turns an impossible search into a handful of sums. There's one gap we glossed over, and it's worth slowing down for. Our grid only stores answers at a few states: 0, a half, 1, 1.5. But when you try a control, it can drop the system anywhere in between. And very often it lands right between two of our dots. Say it lands at 1.25. There is no dot there, no stored cost to go. So what do? We estimate. We assume the cost to go changes smoothly between the two neighbors we already know. So we just draw a straight line between them and read our answer off that line. Watch. At state 1, the stored cost to go is 0.75. At state 1.5, it's 1.5. Our query 1.25 sits exactly halfway between those two. So we walk halfway up the line. Halfway between 0.75 and 1.5 is 1.125. And that is our estimate for the cost to go at 1.25. That is all interpolation is, reading between the lines of your table. It's what lets a coarse grid, just a few stored answers, stand in for the whole continuous range between them. A few dots and a ruler. Now let's write the machine down in symbols, once and for all. A real system evolves continuously, but we chop time into little steps of size delta t. Over one step, the state moves by delta t times its rate of change. Call where you land A sub d, the discrete dynamics. And the total cost becomes a final state term plus a sum of little per step costs, G sub d. Now define the seed. The cost to go at the very last instant is just the final cost. There's nothing left to decide. Then peel back one stage. The best you can do with one stage remaining is the cost of this step plus the cost to go from wherever this step lands you, minimized over your control. Peel back another stage and another. Each peel is simply the principle of optimality applied again. What you arrive at is the heart of the whole subject. The minimum cost with k stages to go equals the minimum over the current control of this step's cost plus the cost to go with k minus 1 stages left. That is Bellman's recurrence. And it is exactly walking backward from h, now written for any system at all. We keep saying solve it backward, try every control. But what is the computer actually doing step by step? It's nothing fancy. 3 nested loops and a running minimum. Let me show you the whole thing. The outermost loop walks the stages backward, 1 from the end, then 2 and so on. Inside it, a loop over every state on the grid. And inside that, a loop over every control. 3 nested loops. Now the heart of it. At one stage, we want the cheapest control. So we keep a single number, call it the champion, the best cost seen so far. And we start it at infinity. Then we try the controls, one at a time. Watch it run for the state 1.5 at the last stage. Try control minus 1. It lands the state at 0.5 and the cost is the control penalty 2 plus the final state squared 0.25, a total of 2.25. Nothing to beat yet, so it becomes the champion. Next, minus a half. It lands at 1. Cost 0.5 plus 1 equals 1.5. Cheaper, so it's the new champion. And we remember the control that won. Next, 0. Lands at 1.5. Cost 2.25. Worse, the champion stays. The remaining controls would push the state out of bounds, so we skip them. The loop ends. The champion is 1.5 from the control minus a half. We write both down, the best cost and the winning control. That is the entire computation for one state. Now repeat that little contest for every state and every stage. As it sweeps backward, the computer fills two tables. One holds the best cost at each state and stage. The other holds the winning control. And there's a nice economy here. To do a stage, you only ever need the table from the stage just ahead. So the machine keeps just the latest column in memory, not the whole history. When the sweep finishes, something quietly remarkable has happened. We never found a formula. We found a table. And now, running the controller is trivial. The system sits at some state, at some stage. You don't solve anything. You just look that state up in the control table and read off the best move. If the state falls between grid points, you interpolate, exactly as before. Apply that control, let the system step forward and look up the next one. Each control is held steady until the next step. So the finished optimal controller is just two simple pieces, a lookup table and a device that holds each control constant between steps. That table is the feedback law we wanted at the very start, the best move for every state. Steering by table. Four things are worth knowing about what we just built. 1. The answer is the true global minimum, genuinely the cheapest plan, not a local dip. Direct search guarantees that, and the principle of optimality is what keeps the search small enough to finish. 2. And it's counterintuitive. Constraints help. Every limit on the state or the control, every wall, every bound, is just fewer options to test. In dynamic programming, restrictions speed you up. 3. The result comes out as feedback, a best move stored for every state, exactly the rule we wanted at the very start. And 4. The catch. To solve a stage, you need every cost to go from the stage ahead, all held in memory at once. For a 3-variable system at 100 levels each, that's 100 times 100 times 100, a million cells. Add one dimension and it detonates. Bellman named it the curse of dimensionality. But look at the cost in stages. Direct enumeration explodes. 40, 200, 800, then tens of thousands. Dynamic programming just walks up a straight line. 40 times the number of stages. Linear against exponential. That gap is the whole reason we bother. So here is the entire film in one breath. To steer anything optimally, solve from the end and reuse every sub-answer you compute. That is dynamic programming. But notice the move we made. We took a smooth, continuous system and forced it onto a grid in time. It worked, but it was an approximation. In part 2, we do the daring thing. We let the time step shrink towards zero. The grid dissolves, the backward recurrence becomes a single elegant partial differential equation, the Hamilton-Jacobi-Bellman equation. And for one beautiful special case, the linear quadratic regulator, we don't just compute the answer, we solve it in closed form by hand. Same idea, no grid. See you in part 2.